continue the problem that we were doing the last time, right? One second. So the problem we were looking at last time is basically, maybe I can put it as a surprising midpoint, right? So this will actually be a theorem eventually, or rather a very useful lemma, okay, problem. So this is, let me call it a surprising midpoint. We will see several applications of this in a few problems I'll do now after we prove this, and then I'll give a few for homework. So what is it? Let's begin with that. So we took an arbitrary triangle, remember? It was nothing special. It was an arbitrary triangle. And then we took an arbitrary line in this, somewhere here, which is parallel, but that's all. Nothing is given about its height, length. With relation to the base also, nothing is given. So it is just parallel. That's all. Okay. Now, basically what we are doing is all what one can do. One second, sorry. There is some technical problem. What is happening? Just a second, sorry. Leave it. Okay. Now we are trying to just use our straight edge. We are not using the compass. We are only using straight edge. What do I mean? I mean that, look, when you draw this extra line, you get this new incident points, right? This new incident points, and you had these old incident points here. And obviously there is another one, right? So in total, we have 5 incident points. What can you do with 5 incident points and a ruler? How can you create more incident points and more lines? By joining some of the incident points that make sense to join, right? So I'm joining this one and I'm joining this one. See, these two are the only ones that I can join, right? I mean, I cannot join this pink one with this that's already joined. You see this thing, this doesn't really make any sense. So I'm just doing least that I can do with a straight edge. And this is a very crucial thing, okay? So doing the most that I can do with a straight edge. So this is like I'm giving a background to the problem, okay? Doing the most that, well, this is just, yeah, that can be done with a straight edge. So you can kind of feel that this is all you can do with a straight edge. So you can use that in problems. Straight edge. So just doing that, we get a surprising result. And that is that this new intersection point that you get, obviously you're going to join that with this if you want to do the most with a straight edge, right? You're going to do this. Obviously, you can keep doing it. You can join this, now you can join this, and so on and so on. That doesn't end. But at this stage itself, we kind of get something extremely interesting, and that is we get that this is a midpoint. Okay. And this is obviously not hard to kind of check for, we take a figure and check it. It's easy. But we want to prove it so that it's always, so that it holds for any configuration without checking. So let me just call it F. I'm not calling it M for now. Yeah. What we want to show is we want to show that BF is equal to FC. So last time we were trying this, we kind of got stuck. Let's try it today. Hopefully we can do it. Okay. And I also try to give a better explanation later. So did you guys make progress in this? Oh yes, yeah, that's what you were saying last time. Yeah. So let's see. So I'll just go with my thing, which we did last time, kind of made these parallel lines. It's clear why we are making these. Okay. So what looks parallel is parallel. I'm not drawing all the things. Okay. And then what? So we have, let's call this G and H. Okay. So here is my question first of all. Is GH parallel to BC? Now this should be easy to decide.
Yes, it is parallel.
Okay, why? Just anyone of you can say why? So why is it parallel? So let's try to do this. So you guys try to prove this. So it certainly feels parallel, but can we get there using the results and so on that we have? Can we derive it from what we know, from what we have proved? Right, but why is DE and GH parallel? Mm, okay. Pragadish, did you understand?
No, I didn't.
Yeah, it's a little, yeah, it's correct, kind of correct, but you have to say it in a more. Mm-hmm. Ah, okay. Now you're putting it nicely, right? Yeah. Now so that we can understand it. Ah. So let's say that this is first pair. So you can use this to explain it. Yeah. So you have a the idea that you're using is very nice, but you have to just put it. Let's say so L1 L1 prime are parallel and this two, and so then what more? Or is this not a good diagram? So we have one pair of parallel lines like this, and we have another pair of parallel lines like this. So let's try. So if we just draw a line, two lines like this arbitrarily. Okay, so then let's use the diagram only and let's try to maybe just remove the things which are not important for this, right? So let's see. So certainly BE is not important and FH is not important. No. So that is important, right? I can't remove it. So then how do we explain it? I mean, certainly we will prove it in a more straightforward way as well, but we would like to understand. So this is one pair of parallel lines. And we have this another pair of parallel lines. And then we have another pair of parallel lines. So how do we reason it? So let's not make GH right now, and let's remove this and try to understand, right? Mhm. Yeah, so that is a should, but that is one has to prove it. So there is one, so there is this which is there, and then there is this, and then there is this. No, but it is not very obvious. Yeah, it is not, like, it's easy to claim it. It is not obvious. So try to do a computational proof. It's not difficult. Try to do just similarity and so on. You can try to do. Meanwhile, I'm just thinking if one can explain it in a easier way. Yeah, so this looks obvious, and basically we'll be proving a very good lemma. That is what I can say, maybe. Yeah. So try to give a computational, like a rigorous proof, I could say. Yeah, so it looks very obvious, right? But then how do you prove it? So later on in the language of vectors, it becomes very simple, but since we don't know that, we will try to do it directly. So Pragadish, do you see that this is something which is now, like, it's obvious to see, especially after cleaning up the things? Yeah. And also second thing is that it's a very fundamental thing. Okay. Like you have these pairs of parallel lines and so on, then you get new parallels along that line. It's a fundamental thing. It's not about this special triangle only. But then let's prove this. Then only we can say this. So it is just has to do with basically ratios. Okay, you have to just basically try to show, you have to just show that AG by GB is equal to AH by HC, right? That's all you have to show. Is it okay if I leave this for homework? Okay, because you can do it if you just sit with it. Like, this is just an exercise. It's like an exercise. It's not a, yeah. So let's assume this. because already we understand it. We actually understand it. We don't not prove it, but we understand. So we can use this. So let us see how we can use it then. Okay. So AG, or you can also maybe say, maybe AD by DG. These are all same, right? Equals to AE by EH. No, I mean, this is not equal. These are not equal, but this is, yeah, this is true. That's just parallels, right? So AD by DG is same as AE by EH. Now, how can we use this? Okay. So eventually we want to show, I'm just writing it here. Eventually we want to show that DG equals to GB, right? Or and that's the same thing as EH equal to HC. I mean, these are all same things, right? BF equals to F. These are all same things. Either one of them, if we can show, then the job is done. Okay. So we already know that DG by GB is equal, so this we did last time, is equal to HC by EH. Yeah, so this is like, this DG by GB, and then that side it reverses. Okay, because kind of like everything is getting, reflected about this point. The D is going to C and B is going to E. And obviously we have shown it. So take this. So how do we use this? So let's see. So we also have these things, AD by AD by let's say AD by DG. You could say AD by DG, right? Is also equal to AE by EH. So this is again just the same thing, right? AD by DG. Okay. That is same as AO by OF. You see just the parallels again, because this is parallel. And then you can take it to that triangle and you can say the same thing, AE by EH. Okay. So what is happening on this side? The same thing is happening. So what's happening on AB to D and G is kind of like the same thing is happening on the other side. Okay. To EH and F in that same order is equal to AE by EH. Sorry, how will it derive? GH. Yes. No, so we are not going to derive GH. See, we are just going to prove GH. No, but we don't need GH. Why do we need GH? Oh, no. This I'm already assuming. Yeah, this is your homework. This is very simple to prove. You have to just take some ratios and subtract some ratios, something like that. Okay. That is a simple thing. So I'm already assuming this. In fact, I've already used this here, right? DG by GB. Is that the right thing to write? Yeah. DG by GB is same as EH by HC. No. So 1 minute. No, so this is what we had done last time. Okay. I am using GH is parallel to BC here, right? So AG by GB is same as AH by HC. That's where I'm using it, right? That GH is parallel to BC, so on. Okay. So now what do we do? How do we combine these ratios? AD by DG is same as AE by EH. Right? No. Equal, no. So DG and EH are not equal. They can be anything. They are not equal. They don't have to be equal. But we are almost there. You see, AD and AE, whatever they do to, means if you compare them with DG and EH, then that is going to be the same as GB by HC. Right? Okay, but then how do we use this? So DG by GB is same as here. Hold on. So DG by EH, that should be same as GB by HC. So yes, but this time it's kind of already in it, right? It's like we have kind of already used them here, right? So no, but you have already used them in a certain way, right? Because BF by FC is same as DG by GB, right? Okay, so no problem. So we are getting that DG by EH is same as GB by HC. That is just coming from this parallel relations, right? But then look at this one and look at this one. Are they the same things? Like something, there is a twist, right? So this we have proved last time, right? That the situation for DG and GB kind of gets reversed when you go to AC, to the AC side, right? It becomes HC by EH. That's so this reversal we had seen last time, yeah? But there is a reversal if we see it from this perspective of O. From the perspective of O, there is a reversal. But if you remove O, I mean, if you remove these things, then there is no reversal. Then we should have then we should have DG by GB is equal to EH by HC. Is that right? Which is what we wrote here. Right? From the straightforward perspective, DG by GB is equal to EH by HC. Okay. Yeah, but from that from the O perspective, it reverses. And that's why it becomes 1. Now you can just even see that from the equations. I mean, EH by SC will become 1. So there is a reversal and there is a non-reversal both, right? So basically we have dG by GB is equal to EH by SC, but then it is also same as HC by EH. I mean, so I'm not just saying it in the air. This is here and this is here. EH by SC is same as HC by EH. So dG by GB is same as SC by EH. That is coming from here last time. And from a straightforward perspective, it is coming out to be EH by SC. So these two are equal. Okay. Now this basically means that it is 1, right? This means that EH by SC is 1. So just try to see if there are any doubts.
Can't we say that what was O before the red dot?
Mm-hmm.
That's the midpoint.
That will be, but how do you prove it? Actually, that yeah. Say the whole thing again. Some quadrilateral.
When you connect
No, they are not always. No, not necessarily. So in fact, you see, GO, yeah. So it's not always true. This is like, maybe you're right. So let me think. Yes, right. But you see, but DO and OC are not equal. Okay. DO and OC are not equal. BO and OE are not equal. GO and OH are equal. Okay, Prakadesh, is that okay? Right? That's what we have seen. But that's what basically we are proving. Okay, that's what we proved eventually. This proof is not such a good proof. We took a very long way. But finally, finally, do you guys feel that there is something very simple in the end? Yeah. So let me try to make it precise, because maybe that's a little difficult if I just ask, find the simplicity directly. But let me say it. What is, and I think yeah, basically it boils down to a parallel to a trapezium, right? I think so yeah, this will be maybe a good way to explain. So already you could see that one perspective it's reversed, one it's not reversed, and that's why. But to make it clear, and Pragadish is also saying something like this, I feel. But let me try to say this in oh no. So you cannot really once again. So, yes, it's all about this. Yeah, it's all, yeah, right. So I think this is a good thing. So let's try to see. This is coming from what Pragatish just said, like from the quadrilateral. So I can just explain everything in terms of the quadrilateral. It's very simple in that sense, right? So if you take this ABCD, it's quadrilateral. So forget about this midpoint here and midpoint here, right? That will just follow. Okay. We just want to look at this picture. Okay. Okay, let's assume this here parallel. Now your job is to just show that EO is equal to OF. And this is in fact much simpler to prove now. Okay, I got this idea. So just Prakadish just said, right, this in the quadrilateral. So yeah, it's not true in the exact thing like AO is equal to OC and so on, right? That's not true, obviously. But Yes, it's much simpler to just see this picture and try to prove. Okay, so show EO is equal to OF. Now that's not very difficult to prove from here. Okay, can we say it quickly? It is true for every trapezium. Yes, this is just a trapezium. Yes, and it is true for every trapezium. Why not? Like, what is wrong with that? Is that anything wrong? No, right? There's nothing wrong with that. It can be true, right? And it is true. It even looks true. And do you agree that this is what we have basically proved? Right, in a hard way, because the picture was very complicated for us. Because see, once we prove this, then when you draw any line like this, right, and if it meets, so yeah, maybe we'll see that later. Okay, we'll extend this to the triangle later, but let's try to prove this. So you guys can prove this, I'm sure, taking some ratios and such, but there is something very simple here. If you take DC, look at the line DC, you're taking the line DC and you're kind of moving up, right? And the length of that line is decreasing, right? And when you move up to this height h, the DC becomes EO, right? DC shrinks to EO. And this shrinking is directly proportional to the height you have traveled. Do you guys agree with me? Yeah. Now see, yeah. Now can you complete the proof? Yes, right. We are starting with the same length and we're decreasing by the same ratio. Simple. Okay. So it was actually something very fundamental, but we just got confused last time. Right? Even this time when we proved it, we took a long way. Okay, but it is fine. You won't always get all the insights at once, right? But this just is an amazing thing, right? I feel. Okay. This is just like, okay, so it's something very true, something very true. Okay, yeah, and I'm sure some variations of this can be given in very interesting ways, but I can't think of them now. Some vague ideas come. There is also a reversal element. It's kind of from here you are kind of decreasing, here you are decreasing, but anyways, leave it because now it's done, so I can't think clearly because okay, we are done. Okay, awesome. Okay, now we have proved this and we have learned. So this physical reasoning one has to do, because just doing geometry from the axioms is not enough, right? I mean, the axioms are obviously abstractions of what we physically want to be true, but the axiom shouldn't be taken as complete in the sense, right? If we have more more intuition for things, we should use them, and we can just write it like that. We can also try to use them to motivate our proofs. Okay, otherwise the proof just happens and then you end up knowing it is true, but you don't really understand why it was true. Now it is just very easy to complete it, right? You join this, and so obviously EO by OF is same as this by this and is same as this by this. So all are midpoints. That is fine. Okay. But I want to show you guys another perspective, which is in fact much more powerful in the sense that it's much more general. And from there, we will prove a very interesting theorem, which will do the last 3-4 problems which we did using ratios. All will be done by like one line or something like that. Means in the sense that it is showing that this basically it will be showing that this calculation of ratios which we are doing by drawing parallel lines, it can be done abstractly once and for all, and then you can keep using it. Okay, we'll see. Because it's follows from such a simple physical thing. I mean, that's the reason why this is also going to have vast implications in that sense. We'll see. So now I'm just taking another perspective. This was how the figure was, right? So let me also remove this AB for a second, okay? Because I just want to explain things. That's why everything is there. We're just drawing what we need to draw. All the lines are there in the plane. AB is parallel to DC. This we have. And we are seeing a surprising coincidence, a surprising ratio, not coincidence. Okay. That there is this M. So there is this M here, and then we are seeing that X, since XA by AD is same as XP by FC, it turns out that DM and MC are equal. Okay. So we want to see it from a slightly different perspective. And we'll see why. So let's say that you are trying to, should I put it? Okay, let's do this. Okay. Let's say that you're trying to balance so assume that this XDC, right? Assume that this is a plate. Okay. It has weight, it has uniform weight everywhere. It's a laminar plate, triangular shaped, anything, triangular, uniform everywhere. And you are trying to balance it. So let's say that you're holding your pencil here, okay, in holding this thing. Okay, so I mean, it's not one of us, it's just someone holding this, and he's trying to balance this. Okay, is this fine what I'm trying to say? So this is the thing on which I'm trying to balance this triangular thing, okay, which has weight now. So now we are interpreting it as a weighted thing, as something which has uniform weight everywhere. Okay, right. So I mean, what does it, is it okay what I'm trying to say? Oh yeah, because I'm not maybe able to explain it very well, that's why. So it's like this, and I'm trying to balance it. Okay, only that this is triangular, yeah, whatever. I can't see myself because of Zoom, but anyways. So, and let's say it doesn't balance, right? I mean, it will not necessarily balance, right? So we're try to balance at O. Okay. I mean, so it will not necessarily, so will it be balanced? No, right? It may fall on one side or the other because this side may have more weight, seems to, whatever, right? So it may not necessarily be balanced. Then you maybe ask your friend to put some weights. That's what you'll try to do, right? You put some weights. Like we used to do this in school, put some rubbers on this side, that side of a scale, and so on, try to balance. And you would have done it also. So, but this is like a 3D thing. It's not 3D, sorry. I mean, it's like a 3-vertex situation. Okay, it's more interesting. Trying to balance. So you'll tell your friend to put some weights on these 3 vertices, right? So there'll be some combination of weights that you can put on the 3 vertices so that it becomes balanced, right? Let's try to understand what those weights are. So let us say that, I mean, so you won't actually know the theorem or anything, right? You just put some weights first. Okay, so let's just say that you put some weight. Let's do this abstractly because I think we can understand all this thing abstractly a little bit. Let's say that you put some weight Wx and you put some weight, let's just speed things a little, Wd, and you're trying to put, so you put a weight Wc and it becomes balanced. Okay, so after you put these weights, it becomes balanced. Then what can we say about these weights? So weights Wx, Wd, Wc make makes XDC balanced. XDC I mean now as a solid thing, not just lines, but it has inner things also filled up, uniform weight. So the question really is, what can we say about these weights? Right? They're not equal. Otherwise, there's no point in putting them. Like they'll still create the same imbalance.
C will be heavier than weight D and weight X independently. MXC is equal to the triangle when you line pink line
Uh-huh.
this will go this triangle MXC.
So, but you see, this pink line is just perpendicular to the plane. So this pink line is like my pen, and this is like this. The pink, this is the pink line. So I don't think you can extrapolate anything about the pink line. Right, you can understand because that's just the way I've drawn it, because you cannot draw that in 2D. Okay, but yes, I mean, I can understand the intuitively that WC should be more than WX. From the picture, it seems like that, maybe. Okay. Yeah, so that I agree with that. But WC being more than WD is not so obvious, and it's not true, I think. Don't assume that M is the midpoint. We are trying to get to that, right? Don't assume. Let's not assume that M is the midpoint. Okay, we will try to get there basically. This says that M is just there. AB is parallel to DC is all we have, let's say. Like even then, we should see if we can tell about the weights, right? Okay, so I don't know. I mean, I don't know the answer. So let's just say that you put a weight of, okay, let's say WX is 10. Let's try to experiment 10, and let's say that, because these things you can kind of measure, maybe, okay. Let's say that XB is 5 centimeters. Maybe I'll just make it 10 centimeters. It doesn't really matter. So let's keep it 5. Otherwise, let's see. And let's say that BC is 2 centimeters. Let's say that XA is 6 centimeters, or it's lesser. So it seems lesser. So 4 centimeters. What can we say about DA? What can you say about DA? Sorry, DA is? Yeah. So let's calculate. Let's just calculate it. 4 by X, and so it's 8 by 5. Yeah. Yeah. So how much is this? No, something wrong. Less than 2, right? So it's 1.6 anyways. Doesn't matter. 1.6. Okay. So now if I've put a weight of 10, and if this is 5 centimeters and this is 2 centimeters, now you guys tell me what, so let's focus on WC. What weight should you be putting at WC? So you want to balance the whole figure. And if you know that is 5, that is 2, then a wise friend, smart friend, what will you put at WC? To get to our goal of balancing the whole figure. Think about torque, right? Balance means that at every point there is really no torque. Are you guys familiar with torque? Okay. Then it's no, but I don't need to use the word torque, right? I can say it. See, so what I'm trying to say is because the figure gets balanced, the whole figure is balanced, it means that the figure is balanced along this line also, right? Figure is balanced along this line. Figure is balanced along this line means that at any point you pick, let's say you pick the point B, okay? And then you look at the total effect of force, kind of total effect of this weight 10 at X about the point B. That's like 50, right? The bigger the XB becomes, the bigger the effect of that 10 becomes at X. Is that obvious intuitively? Yeah, you can understand the door when you try to open it from the, you can understand. Yeah. So the effect of the weight 10 is not just about the weight 10, it's also about the length 5. Okay, so the total effect there is 50, right? Which will be kind of trying to, take X downwards. But then the total effect here will be 2 times WC, right? This side on C, right? But then these two have to be equal, right? If the figure has to be balanced. Is that okay? Yeah. So we must have 50 equals to 2 times WC. Okay, 25. So I think Pragadish had left in between. Pragadish, do you follow this? Yes. Right. Do you know torque? Or you have also not done? Okay, then it's fine. Then basically I'll say it without torque. So let's just say the whole thing. I think it's worth thinking about this several times. So you can go and have a look at, in physics there is something called torque. It's all just same things. See, since we are putting the weights WC and WD and 10 in such a way that the entire figure is balanced, it means that the figure is balanced on the line XC also. Like obviously that also doesn't move, right? Now because the line XC doesn't move, it means that the total effect of the force, like at 10, at X, sorry, and at C, right? The total effect of the respective weights there kind of cancels out, right? Right. So it's like if I put this this phone and so let's say it's balanced. Now it's, what does it mean it's to say it's balanced? It means that like I've put some weights here and I put some weights here and it is balanced. It means that the total effect of the weight here and here is kind of equal, right? Okay. And that should be true for any point. So you put any point B and you try to think about what rotation would happen about the point B, due to those weights. And there should be no rotation. There should be no kind of movement, no seesaw. And that means total effect of the weight 10 at X should be same as total effect of the weight WC at C. But then what's the effect of the weight 10 at X? About the point B, if you imagine the point B is kind of doing the test, right? Balance about the point B. Well, the total effect is 10 times 5, right? Because if you imagine B as the point where we are doing the test, you can take any point, it doesn't really matter, right? But because you're doing it at the point B, right? So you can understand, right? That the total effect of the weight 10 is like 10 times 5. Because the longer that XB becomes, the larger the effect of the weight 10 becomes. Right? That's like natural, right? Because like so you have a door, and so it multiplies that. I mean, that is a thing which has been empirically observed and put as a, yeah. And so basically this 10 times 5 should be same as WC times 2, because that will be effect. That will be the total effect here. Okay. And so then the total torque at B would be 0. The total rotation. So this is not very rigorous. It's just, one can make this precise, but this should be this. And so from here, basically you can determine WC. Okay. WC comes out to be 25. Okay. So it means that here, then you have to put the weight 25. But then you can check that in the same way, this 4 and 1.6, you will see that this WD is also 25. And you can just imagine why. It's the same ratio, right? This will also be 25. Okay. Now this 25 weight here and 25 weight here is balancing this thing along about M. It means that DM and MC has to be equal, right? Because the weights are equal and the thing is balanced. So it can only happen if the length of these two levers or whatever is equal, right? So they have to be equal, whatever they are. Okay, so the weights tell us the ratio also, right? And the ratios tell us the weights. And so that gives us a good way to. Yeah. So just take a few, go over this again. Just take a few minutes. I'm not very happy with my explanation, because it is vague, but I think it's a little too vague. There are some things which is incomplete, which you guys maybe don't see, so it's fine. But I'm seeing some things which are incomplete in this. But it's not really wrong, okay? It's just a little vague. Yeah, to make it precise, one has to actually use vectors. So not doing that, like O has to be taken to be the origin and so on. But since you guys don't know that, then I think it is fine. Okay. So then is it fine? This is okay. So later on, this will become a technique which is called mass point geometry. Okay, it's a very popular technique in Olympiads, but at our level, we don't really need this. This much is okay for us to find simple ratios sometimes. Okay. So, any questions so far? No. Okay. So let us see. But then let me actually try to prove a theorem using this. Let me remove this thing. second. Now I'm not going to take the lines as parallel or such, right? I'm just going to take 3 lines which are intersecting, which are concurrent. Okay. So you have this A, B, C, and you have this D, E, F. Okay. So we have this triangle, and then we have these 3 lines which pass through the same point. That's a very fundamental thing. So our last example, last problem can be seen in this light. Okay, the last problem can be seen in this light. Their AF and their FE was parallel to BC. In this case, it is not such. Okay. So here is a question for you guys. Show that AE by EC, and this is actually a theorem, but we already have some techniques with which I suppose you guys can show this to several degrees of rigor. AE by EC, you see what I'm doing, DC by BD. And then you have BF by FA. What should this product be? It's 1. Okay. I'll try to show this. Now, I'm not, so there's a name to this. This is probably the most important theorem in computational type geometry problems and also non-computational one. Okay. This is called Kiva's theorem, Shiva's theorem, whatever. Kiva's theorem, Ceva's theorem. This thing, now what I want you guys to do is, first of all, if you can prove it, it's very good, but check this for previous problem. Okay. I mean, so see, if this concurrency happens, then, okay, if AD, BE, and FC are concurrent, which is our situation, then this is true. Okay. And the second thing, please do this. Okay. Check this for medians. You guys know what medians are. Yeah. Angle bisectors. Try to do this. Check that for angle bisectors also this happens. And yeah, why not altitudes? Because that's even, I think, yeah, you can try to use Pythagoras theorem to find those lengths. You can do that. Or if you know trigonometry, you can do that. And then check that this ratio happens. This ratio is true for those cases. It's very easy. You should do this. Okay. Because it's not just true, it's just true in a very nice sense. Just check these things. And maybe try to use the weight reasoning to explain this. Use the weight, like, this is the ratio. If I put a weight 10, then what weight should I put here according to the ratio AE by EC? You can try to put a weight here, and then you can get the final ratio. So try to just see. Okay, basically what I've explained, try to see if you can apply it in this case. Use the weight reasoning. So I'm breaking this up into several things so that at least a few parts you should do. Try to spend at least an hour on all of this. You'll get a few things. Okay. So for now, this 3. Yes. So let's keep it here. I'm not going to go into the proof today, the rigorous proof. That's not very important for now. So this is fun. You can try all these things. And obviously, you can also use the reasoning. I mean, BD by DC, you can actually prove it actually. BD by DC is same as ABD by ADC. Using those things, you can actually prove this product is 1. but it is. Now, actually, it is more is true. That is, this is one if and only if AD, BE, and FC are concurrent. I'm not asking you to prove it, I'm just saying it. Okay. Basically, if you know two of the ratios, then you can know the entire weights that you have to put. And then the last ratio turns out to be the opposite, the product of those two ratios. Okay. But then if these three are concurrent, then this is true. But also if this is true, then it implies that these three lines will pass through the same point. So you can imagine that it also will help you to prove that things are concurrent. So it's a very nice thing. Okay. So any questions regarding this? Something that you find very strange or sudden? No questions? Okay. So let me then end with another series of questions. I'm asking these questions now in context so that you can see the connections and try them as soon as you, in the sense that don't wait till last day of, try earlier, you refresh, you'll know this and you can kind of connect with what I'm saying and what you can try. Now I want to say certain things based on applications of the first result we proved. Okay. So applications of the midpoint theorem. Let's just call that the midpoint theorem. So for that, here is the question number one. So let's say that I take a line. Sorry, I'll take a line later. I'll take this triangle. Okay. Let's say that I take this triangle and then I take an arbitrary line which is parallel. Sorry, I take an arbitrary line which is parallel. Okay. And then I take this line and I do that what I did earlier, join the opposite things, and I get this point. Okay, point P. This L is parallel. Question is, as L moves, okay, how does the point P move? As L moves means as L moves up and down, remaining parallel, the point P will keep changing, right? But how does it move? What path does it trace? So you can try to check it. You take another thing and you get another P, you take another thing and will you see some very interesting path, or what will you see? Will you see a line or what? Let's get some idea of this now, because this is not very difficult. Now this is another, just before you think a little bit, as I say, this is another type of question, locus problems. You will meet more of this in coordinate geometry and you'll keep seeing them. Another dynamic aspect of geometry. So actually we have already answered this question actually, in some sense. So just think. So as the line L is moving up and down, you can just actually just do it now on your paper and see. You can just take two, 3 lines parallel and you'll get the different points P and you can see what kind of shape they make. Do they make a straight line? Just think.
Connect, yeah, we connect A to B and then
That is a line. Ah, nice, nice, nice. Okay, so let's see. Ishana, what do you get? Okay, so now try to prove it. Okay, it is this line. It's actually, we have already done it because, let me not say, think. Okay, the answer is correct, but you have to give an explanation. You can see how this is directly related to what we have done already, right? This is thing. So it's like you kind of see it, but then, and you also know it's connected, but maybe you don't see the answer. So you don't see the reasoning directly, but think you'll get it. Another question. Let's say that I give you a line and I give you a point. So this line L is given and the point B, some point X is given. Okay. Now, using a compass, this is, you would have done already, but you have to do it. Should be good to do. Using a compass and straight edge. So straight edge means just a straight edge, not allowed to use measurements, though it's not even very useful actually. But using a compass and straight edge, okay, make a line. You can see what I'm asking from X. Again, this seems very much related to what we have done, parallel to L. So this is a very simple question. You can, this is a fundamental construction. You will be able to do by perpendiculars and so on. You can do it. And you know how to make perpendiculars. If not, then try to see. It's like a school question in that sense. Try to see, then we can discuss it if you cannot. But the next thing is, do the same without a compass. But do the same without a compass if do the same without a compass, assuming the point M midpoint of L is given to you. Okay, so you are given, so I'm taking away the compass from you, but I'm giving you a point. Okay, I'm giving you a point M. So you use this point, you can use this point and you can kind of see, this is again related, right? Now the midpoint is given, not the parallel line, but the midpoint is given. You need to make the parallel, right? The midpoint is given. So this is the midpoint. You can assume it's a midpoint. You can use this and try to get a line parallel, but you're not allowed to use compass. You're only allowed to join things that you have or just draw some lines, draw any number of lines, but I want a line in the end that will be parallel. Okay. So any questions? Straight edge. Straight edge. Yeah. So using compass and straight edge, you can do it. You can just draw perpendiculars and so on. Maybe try it though. May not be straightforward. I don't know. and then do the same thing without a compass. Okay. So you can see that the problem that we have solved, we have basically constructed the midpoint without a compass. That is the reverse question, right? How? It's like we had a line and we had another line parallel to it. Okay, okay. This was given to us. Okay. And we basically constructed the midpoint without the compass. How? I said, okay, I mean, I don't have anything. So what will I do? I just make a triangle. Any triangle I'll make. Doesn't matter. Any triangle. Just take a point and make a triangle. I'll say, okay, what can I do? I want the midpoint of this L. Now I want to make the midpoint. I'm showing how what we have done is the reverse construction of this, what I'm asking you to prove. So what we have done is we have given two parallel lines and a line, yeah, parallel lines. I'm constructed the midpoint of them. So I'm trying to explain how we've actually already done it. So once again, given two parallel lines, I say, okay, I only have a straight edge. So I just make a triangle, any triangle, right? And okay, only straight edge. So what can I do? I can only join things, which join some intersection points, right? Right? Okay, only straight edge. So if someone also doesn't know anything, like just don't know anything, this natural to just draw this. Ah, okay, this should be the midpoint. And we have proved that that is the midpoint. Is it okay? Yeah. So we constructed the midpoint. That's why it's a surprising ratio, surprising midpoint, right? We have constructed the midpoint using only two parallel lines and only a straight edge, no measurements. No compass and no measurement, no compass also. And we got the midpoint. I'm asking for the reverse. Okay. It's not hard. It's not like another question actually, but you have to think. So I think these are enough questions for you guys to try. Okay. So yeah, just try them. And then when we meet next time, we'll discuss them. Okay. So I plan to take a few more